Welcome all. My name is Darren Lerner. I serve as the University Consortium Director here for PICASC. And for anyone joining us maybe for the first time or hasn't interacted with us as of yet, I'm getting a message. We can hear you, but you should mute your mic. Okay, hold on. 1 second. We're just working out some of the tech. All right, that's good. Technical, thank you, Chip Fletcher out in the audience, giving us some helpful pointers as we work through the first hybrid seminar that we're running here. If you are joining us for the first time or you haven't interacted with PICASC yet, the Pacific Islands Climate Adaptation Science Center is a collaborative partnership between the U.S. Geological Survey and a university consortium, which is hosted here at the University of Hawaii at Manoa, and with the university partners at the University of Hawaii at Hilo and the University of Guam. And we're designed to support sustainability and climate adaptation in communities across the Pacific Islands. This Slice of PI-CASC seminar series is aimed at providing a platform for sharing ongoing and state-of-the-art climate adaptation research and science to management applications in Hawaii, the U.S. affiliate Pacific Islands, and beyond. So our speaker today was born and raised a long way from the ocean in a small town in the foothills of the Appalachian Mountains of North Carolina. Dr. Phil Thompson, who I know many of you know, received his BS in physics at North Carolina State University and his PhD in physical oceanography at the University of South Florida. Dr. Thompson is an assistant professor in the Department of Oceanography here at the UH Manoa, and he serves as the director of the University of Hawaii Sea Level Center. He also serves as a principal investigator for research projects funded by USGS, NOAA, and NASA, all focused on understanding decadal climate variability, future tidal flooding, and the interaction of sea level and waves in the nearshore environment. An emerging theme in his work is the co-production of research that facilitates science-based coastal management tools that support effective science communication. Away from the daily grind, Phil enjoys playing guitar and learning new programming skills, which I have to say, maybe he needs a little help understanding being away from the grind. But he does also greatly appreciate his time with his family. And Phil has a bit of a secret that we all need to help him keep about his Lego skills, apparently. His 4-year-old thinks that his dad is the best Lego builder in the world. And Phil's really hoping to keep that title for as long as he possibly can. Phil, thanks for joining us and bringing us a slice of PICASC today with your presentation. The title of Phil's talk today is From the Moon's Wobble to Augmented Reality, Understanding and Communicating the Impacts of Sea Level Rise in Hawaii. For everybody online, I'm hoping things are coming in clear. Please do use the chat if you see or hear any difficulties, and we'll try to react to that. And otherwise, take it away, Phil.
That's cool. First talk I just told Darren earlier. This is the first talk I've given in person in like 2 years. Yeah. So I can't tell if I'm nervous or like excited or whatever. But it's really great to be here with the PICASC folks and Sea Grant folks and to see you in person. So let me send you to my screen's not being shared.
It was. I'm not sure what it came on.
So one thing that's going to be challenging here is that my pointer doesn't show up when I move it. So if I start talking like I'm pointing at things and I forget, then please somebody let me know. You can't see my pointer. I'll do my best just moving my hands around. So yeah, I'm going to talk about understanding and communicating the impacts of sea level rise in Hawaii. And most of this will be talking about things I've done with PICASC, this great group of folks here in this room and online as well. So I thought maybe the first thing that we could do is just start with a little bit of global context. because the IPCC AR6 report just came out, and it's a little different than last time around for the AR5 report. Now they're using something called shared socioeconomic pathways. And I just put an example here on the right side of some of the carbon dioxide curves going out in the future. If you're curious of what sort of some of this terminology means, so this is these numbers here. They're again on pointing. Oh wait, it's not advanced on the.
So,
you're saying this slide
yeah,
advanced?
I think you shared your desktop rather than the PowerPoint, which is why we're seeing.
Yes. Exactly.
So unshare.
So, yeah, unshare and then reshare just your, this is the keynote.
Okay, sorry folks.
No
Just
worries.
working on some bugs here. So if I share. Yeah, I shared this. But if I hit play,
But it's not in
see if the screen's not advancing. This was working 5 minutes ago.
Apologies, folks, we're gonna get this
Sorry
worked
about
out.
that. Let's see.
But that's fine, it's changed.
It's not going back.
Your volume, your mic is on.
Now my phone's working, so that's good. Some word came out of it. That's good. All right. Okay, let's try this again. So I'm just looking.
Your
You have
mic's
to
on.
mute your computer.
Oh, I'm muted.
It's off.
It's off.
It's muted.
Is that
Is that off?
Yeah, that's all.
Echo's gone now.
All right. Well, it seems that all the technical issues have now resolved themselves somehow. By chance. So here we have, let's see, where was I? Right. So we wanted to just provide some global context and looking at what's coming out in the AR6 report. So just to give you a little bit of background on terminology if you're not familiar. So these numbers here on the end of these SSPs, these are the radiative forcing, so they're watts per meter squared. So if you think about like at the top of the atmosphere, the overall solar radiation coming in on average, it's like 340 watts per meter squared. So this is like, if you go from like 4.5 to 8.5, it's like 1 to 2% sort of level changes. And how they correspond to various amounts of surface warming. And of course, methane and other greenhouse gases and aerosols are also included in these scenarios. So what do these mean for sea level? So here's another figure from this new report. And again, there's something a little different here. So if you look at the AR5, so here we have this business as usual. So here the 8.5, this is like business as usual. Here is another scenario where we have some more success at mitigating our greenhouse gas emissions. But if we look at the AR5 versus the AR6, this is the last report, 2050, not that many changes. And even if you go for a lower emission scenario, it's relatively the same, something like 20 to 30 centimeters by mid-century. If you look at 2100, however, things are a little different. And the main difference here from what IPCC did before was they've included some of these low confidence processes, things like marine ice shelf instability, where previously they focused more on medium confidence processes, things we think we understand a little better. What that does effectively, though, is it gives you this long tail of uncertainty at the high end on this scenario here. So AR5 or this intermediate report here, you're looking at 0.5 to a meter, 0.5 meters to a meter of sea level rise globally by 2100. But with this new report, there's this long upper tail where some of these processes that we don't think we understand all that well yet, or we don't know how to model them very well yet, could potentially lead to a lot more sea level rise in the future. That is uncertain. And so this is a good example. This is an awesome video, if you can see this well, from paper last year, opinion to a paper last year, showing the flow of the glacier into the ocean and how this works. But the concerning part here is if you look at some of these areas along the grounding lines of these glaciers, here, these insets, you can see some of the shear going on here and some of the breaking apart of these areas that weren't previously flowing through the ocean. So some of this breakup is showing signs of structural weakening. So some of these ice sheets may be disintegrating as we speak. And so some of these upper bound scenarios could be quite possible given what we're observing. So that's kind of on the global scale, but of course there's spatial differences. And one of the things I wanted to talk about a lot in this presentation is the things that contribute to differences around the Pacific. Why are not only the sea level change, not only the amount of sea level change different or the rate, but also how the impacts are different. And so here's the map of sea level change from this report. You can see that the darker colors here, these are greater amounts of rise. So comparing like California and Hawaii, for example, California, something like 0.7 meters, Hawaii, in meters. So looking at like roughly a third more in Hawaii, and you can see a lot of spatial structure around the Pacific and how this can differ. There's lots of contributions to these differences. Ocean atmosphere dynamics, changes in ocean circulation, changes or spatial structure due to the gravitational and rotational effects of ice melt. You've heard of ice melt fingerprints before. So the gravitational pull of the ice sheets is so great, there's so much mass that actually distorts the ocean surface, and when they melt, that distortion goes away. And that leads to spatial structure and sea level change. And of course, there's vertical land motion as well. You can get a sense here of the different patterns associated with these different contributions. Each contribution here in the map is shown as a time series here on the left. So you can see going from 2020 to 2100. These bars out here are the uncertainty. And when you see this big orange bar here, that's the uncertainty in the Antarctic ice sheet, and that's related to those instabilities that we just talked about. Now, one thing that the IPCC has done differently this time, that they did not do before, is they've included vertical land motion in their maps of sea level change. I think for those of us working in the Pacific Islands, it's probably important to note that this may not be the ideal methodology for what they've included here for the Pacific Islands. The methodology here is probably more applicable on a broader scale, like continental scales, regional scales. And I think it'd be really important to critically take a look at the vertical land motion component of this if you're working in a particular island or coastline in the Pacific. And of course, this is really important, and this is sort of my first tie-in. It's really more of an advertisement because we haven't done much yet. But this is a fairly new project with PICASC, where we're looking at how the sea level rise in American Samoa is going to evolve over the next 20, 30, 40 years because of this earthquake that occurred in 2009. There was an initial offset. So here you can see in blue a time series of sea level relative to the center of mass of the Earth. And then you can see what's actually measured at the coastline in yellow and red here. And so there's an offset, and that offset is growing in time. That's because the island itself is now sinking after that earthquake. This is GPS data here showing that sinking. These are different model runs given different viscoelasticities of the mantle in that region. But the idea, basically, the takeaway is that 30 to 40 centimeters potentially more sea level rise in American Samoa, essentially double what the climate projection would be for that particular community over the next 30 to 40 years. And that's a big deal. And so this is just another way of saying that treating this problem as local is really important, and thinking about how the effects will evolve differently from place to place. So now what I want to get into is that was kind of how sea level rise is changing and what we expect to see, and how it can be different from place to place. There's also differences in how the impacts will emerge. And a lot of that has to do with the different tidal regimes that are present around the Pacific. So this is just some screen grabs of the last 6 days from the NOAA site of the tide predictions and the observations from Hawaii and from Pago Pago in American Samoa. There's very different character here, right? So in Hawaii, we have a mixed regime where we have 2 high tides per day, but one is a lot bigger than the other, a lot higher than the other. And in Pongo Pongo, there are two roughly equal high tides per day. So they have more of a semi-diurnal, or twice per day tide. We have mixed, but with strong diurnal, or once per day component. And that impacts how the sea level rise impacts will evolve, because they map onto different types of long-term changes in the tidal variability. So I thought it might be kind of cool. So this is something I've been working on a lot with my family from PICASC and thinking about. And I thought it might be interesting to go through why some of these cycles exist. It's fun to think about. For one thing, thinking about the alignments of the sun, moon, and Earth. So there are very predictable but long period changes in the tides themselves. I forget the old code. What is it, like death taxes and tides or something? They're all constant. Well, not really, actually. The tides do change on long time scales, and so these changes are related to natural cycles in the orbits called recessions, the changes in the orientation of the orbit. So let's think about how some of those work. Actually, first let's just look at some data from Honolulu. These are the monthly maximum astronomical tides. So nothing going on with the ocean dynamics. This is just the astronomical part. These are monthly maxes from now up to 2050. Highly predictable tides. So the interesting thing to note here, though, is you see a couple of different timescales of variability. You can see this kind of long oscillation here in the maximum tide, and that's at 18.6-year period. There's also some shorter variations here at a 4.4-year period. And the main takeaway really for me, though, is how large these changes are. They're not negligible, and in fact, they are as large as current sea level rise, if not larger. So here, the amplitude of the largest tides changed something like 7-8 centimeters, decreased from 2006 to 2015. But the mean sea level during that time only increased by a couple of centimeters. So this more than canceled out the impact of sea level rise during that period on the frequency of high tide flooding. But of course, this is an oscillation, so it goes both ways. So sometimes it cancels out sea level rise, and sometimes it adds on. So this creates, as you'll see, some inflection points in the impacts going forward into the 21st century. So this is probably something most of you are aware of. This maps onto the King Tides project as well. So here we have, you're probably well aware of when we have new moons or full moons, everything's in alignment. This is when we get our spring tides, roughly twice per month. There's also perigean spring tides. So the orbit of the moon around the Earth is elliptical. And so there are certain periods of time when the moon is closer to the Earth than others. So that creates a larger tidal potential and time range. So when you get the moon at its closest point to Earth around its orbit, so perigee, at the same time as a spring tide, you can have a perigean spring tide. These occur roughly twice per year. So that's typically when you get those notifications from sea grants, like they grab your phone, go out to the beach and take some photos of impacts. But there's other layers that lead to these long-term oscillations. So another impact, not just how close the moon to the Earth comes, but also its declination. So what's the angle? So if you pointed a line from the center of the Earth out to the sun or the moon, what is the angle between that and the equator? So that impacts whether or not you're emphasizing once per day tides or twice per day tides. So in this case, we have a pretty large declination, and you see that the tidal bulges here are at a strong angle. But the Earth is rotating around this way. Right? And so you can see that on this side of the Earth, we have a relatively large tidal bulge, while on this side we have a relatively small. So that's mapping onto a diurnal or a once per day sort of tidal regime. Now, of course, in the real ocean, we have continents in the way, and the tides can't keep up because the Earth is rotating too fast. But in terms of understanding the basic idea of how these types of tides are enforced and what the reason for these cycles, this is a perfectly fine way to start thinking about it. So when you have a small declination, so if this angle were to get a lot smaller, then you would start to see those bulges be more equal as the Earth rotates under them. So you have more of a semi-diurnal, whereas this is more of an emphasis on the diurnal. So it's like a give and take. One occurs at the expense of the other. So when we start to think about these long-term cycles, though, it's also important to note that the solar declination has a minima at equinoxes. So we have winter in the northern hemisphere. We have a large diurnal, so there's a big tilt of the sun relative to the angle of the equator. But at the equinoxes, you can draw a line straight from the center of the sun right to the equator. You can actually connect 2 points there. And so we have a minima and a declination, but a maxima in the twice per day tide. So then the question becomes, how often do we have a perigene spring tide at the same time as an equinox? And that time scale is dictated by what's called apsidal lunar recession. And that was a rotation of the precession of the Earth's orbit. So if you think about an axis, the long axis along this egg shape of the orbit, this axis is rotating in time, and it rotates once every 8.85 years. So half of that period, we get a perigene spring tide at the fall equinox. 4.5 years later, we get a perigene spring tide at the spring equinox. And so there's a 4.4 year cycle in the tidal extremes due to that declination and also due to we already talked about the spring tide and perigene. So the other cycle we haven't talked about, this was a little trickier to visualize, is the 18.6 year nodal cycle. So this one, we have to think about not just the orbit of the Earth, but the plane in which the orbit is occurring. So that precession we just talked about, that one is occurring within, along this orange circle here. It's occurring within that circle. But the plane of that circle is actually orbiting around or precessing around Earth as well. And you can kind of think about this like you spin a coin. Right before the coin falls flat on the table, it kind of goes, it's got that kind of flat thing. So that sort of rotation like this, that's kind of what the plane of the moon's orbit does in space. And it goes through one rotation every 18.6 years. Before, we talked about the declination of the sun relative to equinoxes. This one changes the declination of the moon. And it maps onto diurnal tides, particularly here in Hawaii, very strongly. That's why we see the 18.6 year cycle of Hawaiian tides quite prominently, as well as a lot of other places around the US. So this is just what I was saying. So due to that sort of coin rotation sort of motion, that flat rotation of the plane, then this angle here between the Earth's, the lunar orbit and the equator changes plus minus 5 degrees every 18.6 years. And that leads to that nodal cycle. So hopefully that wasn't too much like a PIs 101 lecture, but I just think it's really cool to understand where the cycles come from. Certainly none of this is new, right? This is we've known about these for hundreds, if not thousands of years, but I think sometimes it gets lost in all the climate literature, and I think it's interesting to come back to the tides because it really is where the impacts occur. So this is just showing that same thing from earlier, just to hammer that home, right? So that nodal cycle, we have the 18.6 year cycle, and then we also have the shorter 4.4 year cycle. And depending on your tidal regime, so places like American Samoa with a more semi-diurnal regime would tend to get more of that 4.4, whereas the Honolulu gauge with its diurnal regime, or almost diurnal regimes, would tend to get more of that 18.6. Okay, so let me talk a little bit about the research that I've actually done in this and incorporating these concepts into projections of impacts and high tide flooding in the future. I won't spend a lot of time on this, but the general idea is that if you have, there's two ways to have some period of time. This is a year of data. I think it's from Honolulu. But the point wasn't where it was from, just to give a general idea here. There's two ways to do this, and it's kind of obvious. You either can raise the average level of the water, which would be like a mean sea level anomaly. So some anomaly due to El Nino or an eddy or something like that. You raise the average level, or you can change the tidal range and change the actual height of the astronomical tides as well. So what we did is we come up with a statistical model that takes the mean sea level and the tidal amplitude essentially, puts them into a statistical model and figures out what's a likely range for the number of high tide flooding events you would get given those two inputs, given all the other unknown and random variability that's out there. So this is everything we put together. We have this framework that we developed that was initially developed with PICASC funding, specifically focused on Honolulu. Since then, I've expanded this to the rest of the US with funding from NASA. And so this is our framework that we developed with random sea level variability for El Nino, trends obviously from the projections, then the astronomical tide projections out to the future. Put it all together, give a user a threshold, and get out some projection of days into the future. So let's look at what those look like, and I'll come back to the Pacific Islands here in just a moment. But this is a figure from a paper that was published earlier this summer. So this focused really on the entire US coastline. And one of the conclusions here, when we actually did these projections, was that there are inflections due to that nodal cycle, that 18.6-year cycle. There are inflections in the projections of high tide that can serve as really important planning horizons when you're thinking about when are the impacts from sea level rise going to really ramp up. And it turns out that around the mid-2030s, at many locations around the US, Gulf of Mexico, west coast of the US, Pacific Islands, or I guess specifically Hawaii, really, the mid-2030s is a really important inflection point in terms of impacts. So these are projections of the high tide flooding in days per year for a particular sea level rise scenario, the NOAA intermediate scenario, with a little bit of a range of possibility for any given year around that. That's due to the other kinds of variability we put in, whether or not it's an El Nino event or other kinds of variability that might be affecting any given coastline. So this made a little bit of a splash this summer, and it got picked up by quite a few news outlets. I think, unfortunately, I may have peaked as a scientist because of that. This work made the cover of a tabloid in the UK, which I think I'm just going to frame this and quit. That's a hilarious news going but yeah, so what I want to do now, though, is take what we have done for that whole US coastline. I will definitely make figures for this talk for 4 US affiliated Pacific Islands. So here we're seeing Honolulu, Guam, Pago Pago, Kwajalein. And this idea of like I mentioned before, where you have more of a semi-diurnal range, 18.6-year cycle is less important. In fact, the 4.4-year cycle is more important. And so you don't see those same inflections at most of the Pacific Island locations, like you do at Honolulu and some of those other locations around the West Coast line. So it's interesting to note that. But there were other aspects of that analysis that kind of got lost in the whole new model thing. And that was another important one, was the clustering aspect of this. So whether or not, so if you wanted, someone's making a decision about coastal planning, and you give them some information about, okay, there's going to be 20 events on average in 2040s, right? What do they do with that? I mean, if you actually average that out, it's very few per month. Right? But in reality, that's not how these events occur. They don't occur evenly distributed over the year or over the years. In fact, there are particular months, particular years that are more severe. And that is the frequency of impact that you really want to plan for. So this idea of clustering is really applicable here for these Pacific Island locations. So basically what I was just saying. So yeah, so what if those events that you're getting some projection, what if those are really concentrated in a few months? And so how do you adjust your planning strategies to account for that? So a first aspect of clustering is just the seasonal variability. And we know that already here in Hawaii. This is why we have our king tide surveys at particular times of the year. There are certain times of year where you get more of these events. And so one of the things we've done is we've done the projections by month into the future. So you get an idea of how these are distributed through the year as the projection goes forward in time. So looking at Honolulu, 2035, maybe a handful here and there around, but as you get into the mid 20th century or 21st century under this intermediate scenario, you can see how these, how the seasonal variability, how these events are distributed throughout the year, and that will change a little bit. Remember, because that perigee spring tide is not exactly twice a year, it's like every 7 months, so it's going to change a little bit from year to year when that variability will occur, or those impacts will occur. We also see how different it is from place to place. It's almost completely different on every one of these locations, how these events are distributed within the year. Honolulu kind of has this fall, late summer kind of centric look to it. Tonga has this almost really nice semi-annual cycle in 2050. Guam, everything's kind of scrunched there in summer months. And Kwajalein almost is sort of uniform across the world. So again, it's really important to take the local factors and the local tidal regime into account when you start to think about how you plan for these. What are the relevant frequencies of impact that you expect to see during a given year or an extreme month or season? So then what we did, so kind of building on that, is then to say, okay, so what happens with, what if you get an El Nino event at the same time as your peak high tide flooding season, right? So how many could you possibly get during these extreme periods of time? And so here you can see how important this clustering aspect is. So each of these dots represents a different type of frequency. So the blue ones are 5-year averages in these pentabs, or 5-year periods, early 30s, late 30s, early 40s, and so on. The blue is the average number of events per month over each of those 5-year periods. The orange is the peak season, or what would be our prediction for the worst 3 consecutive month period. And then the orange, or this kind of reddish color here, would be the most severe month in that 5-year period. So if you just rely on like an average number, and you look at Guam, for example, you would get something like, okay, so maybe like 2, 3, 4 per month or something in the early 40s. Maybe that's not, maybe that doesn't seem so severe, and maybe it's kind of easy to overlook that, and maybe wait for a later planning date. But when you actually think about what is the most severe month or season going to look like, the most severe month, we would expect to see something like 20 to 25 days per month, right? So well more than over half the days in a given month during this 5-year period at some point. So then what do you want to plan for? Do you want to plan for, be ready for that 3 or 4 per month? Or do you want to be ready for that really severe season per month? That gives a lot more. So thinking about how the tidal regime and the other types of variability maps onto the frequency of impacts is important. That's what we're trying to do. So then, I already talked about how the nodal cycle impacts planning horizons, but also this idea can impact planning horizons as well. So again, this is kind of showing the timing of when you would expect to see high tide flooding on more days than not in a given location. So that seems like probably something you want to be well ahead of the curve, so to speak, before then. So if you just think about when you get more days than not expected on average over a whole year, for all these locations, you're thinking something like the mid-2050s. You got plenty of time to get things ready before then. But if you start thinking about this clustering aspect and working your way down and various different probabilities and timescales, the timeline moves forward quite a bit. So if you think about, okay, so instead of over a whole year, when do we expect every year to have at least 1 month with more days of flooding than not? Now you've moved your timeline ahead about 10 years. If you think about when would be the first time you would have a month that would have that sort of frequency, more flooding days than not, then say a 50% chance by probably looking at sometime in the 40s. You can see that the Honolulu gauge is now starting to separate, where these clustering 4.4-year cycle is more important here. So you're getting that shorter time scale of tidal variability. Also the other types of extremes, suitable variability that occurs in these locations. Honolulu is now kind of lagging, whereas the timeline for these other locations is moving up pretty rapidly. And by the time you allow for, okay, I'm I'm not comfortable with more than a 25% chance that we're gonna have this frequency by a given time. We should be ready by mid to late 2030s for these locations for this intermediate scenario. This idea of clustering and thinking about tides and how the tides and seasonal variability and other anomalies kind of can produce these severe monster seasons changes the frequency that you plan for and also the planning horizon, the timeline. So currently, you can view some of these results from the US API, but not some of the other Pacific Islands, on this NASA tool. A lot of the PICASC research and also NASA funding research fed into. There will be a new interagency report coming out at the beginning of this year. So there's no scenarios everyone's been using. They're going to get an update. This will be NASA, NOAA, USGS all working together on this. There'll be a lot more locations in it, not just the US coastline and not just the US API. So there'll be other locations that we do this. And what I'm going to try to do this year is to, with PICASC funding, create a viewer to look at these flooding projections for all Pacific Islands that those projections are available for, and to use and actually incorporate some of those new types of figures I just showed you, the analysis. So for any given location you're interested in, you can go and browse those figures and get a handle on how clustering and tidal cycles impact. All right, so I've got about 10 or so more minutes. I'm not sure when Darren's going to pull flood on me. But the last thing I want to talk about here is, so we talked a lot about how important it is to have local focus, right? So we took this big view and pointed out how different locations are different. So then what about actually doing local targeted analysis? So this is, I want to spend about 10 minutes here just talking about now National Historical Park, where we have a PICASC funded project to try to understand how sea level rise and waves and are combining to already produce impacts in this park, but also how that will evolve into the future. This has been really fun so far. There's more fun to come, I guess. But it's been a great interdisciplinary project. We've worked with the Park Service here. This is Mary Ann. She's an archaeologist at Willow, and it's been amazing in helping us work through our data collection. So what we want to do is try to provide them with and co-develop some science that allows them to assess the vulnerability of those really important cultural and beautiful assets that are in this park. They're already noticing that there's impacts already. The impacts are getting worse, and so we're trying to project out in the future just how that will evolve. So the first step in here was a LiDAR and structure from ocean survey that was done by USGS CONED. Jeff Danielson and Gesh and others came out and did a fantastic survey with drone-based LiDAR, photogrammetry. And this supports a number of aspects of this project, from wave modeling, which I'll show you just a snapshot of in just a moment, being able to depict how this innovation affects the park, and then the capstone here of this talk, I'll show you one of our really nice visualization tools that we've started to develop. So inundation modeling, that's going to be done by my graduate student, Ashley Sanchez. And so we put out a number of water level sensors around the park. And again, Marianne and her team and Sally Beavers, also at the Park Service, have been amazing in helping us get this done. So we put out these sensors, and we've got all this water level data that we can then use to validate our model. This is just a snapshot of what that model looks like. So this is a really awesome. We've been able to use the total bathymetric data from USGS CONED, and we've used the in-situ data that we're starting to use the in-situ data to validate this. We run the wave model over the total bathy, and you can actually see the different braking zones coming in, the waves, and if you look really close, you can't really see it that well here. It's a pretty big swell in the region, actually. You can see some lines of inshore sea and swell wrapping into this cove area where they're starting to get the impacts. And this also allows for wetting and drying cells, so we can actually see the setup and the recommendation coming into the park. So we'll be folding that into some of our sea level analysis for the area that we've already done. Let's see. All right, cool. Yeah, I've got a few minutes here, so this is shiny. So the last thing I want to show you here is something that we've been working on again. We've used some of that, like I've already mentioned multiple times, that amazing imagery and bathymetric information from USGS. And what we've done is we've used our in-situ observations to connect that elevation data with the sea level rise scenarios that we have. We're able to map in a three-dimensional way and using augmented reality the sea level rise within the park. So I think at this point, it's probably safe to say this is really more of an outreach tool. I think it's really cool to be able to help people to kind of understand general timelines and extent of impacts of sea level rise in the park. Hopefully we can make this even more robust once we get our wave-driven contributions in there, thinking about the new scenarios that are coming out, some of the statistics that Jeff and Dean are doing at USGS Code as well. Now, I want to give you a quick demo here. You can actually download this on the iOS App Store now. It's just approved this past weekend. There will be a version for Google on the Android App Store, and that should be it's pending, so it should be approved any day now. But let me just this out. Stop sharing really quick. Am I still good on time there?
You're fine. Yep, doing great.
Let's stop sharing. I don't think I actually said his name, but
Interesting that it does that. Huh?
Your iPhone, where do you get it?
so Manya Kumar is the developer of this. Like I said, he incorporated all that imagery and DM information. In the middle of the floor. And you can, if you want to decide and move it around, you can move it stuff into your fingers. But then once it's there, this is like a virtual model in the middle of the room. So you can type that. An intermediate scenario here, you can start to see where the future. So there's two levels here. One of them, so the blue level is kind of your typical high tide. And then there's a red level here, which is your extreme high tide. So they define that as something like 2 to 15 times per year. So you can see that there are already areas here around the payout here, where there's a lot of inundation around 2 to 15 times per year, so a few times per year. But it's important to know that in addition to just changing sort of the average high tide. So that's one of the tools that we've been developing. We're hoping to add some more functionality to that. Specifically, starting to sort of walk away, come back to it, it's still there. You turn on some sites, and right now there's some sites here that basically just give you some information about the park asset, but we're hoping to provide some specific inundation statistics for these locations as well. Yeah, so definitely try to give that a download and probably making you sick here now that I'm walking around. Yeah, so definitely give that a download if you can. You can just search sea-level AR in the iOS App Store. You should be able to find it and download it. But yeah, let us know what you think. Definitely get in touch. So it's not there. I'll do.
That's great, thank you. Not only dog applause, nice and done. And you have some online as well. So we do have some time for questions. I had put in the chat earlier, please do, if you can raise your digital hand, if you're online under the reactions there, you can throw a question in the chat, and or we've got folks in the room and one dog who can ask questions as well.
The sea level AR visualizer, is that the
Yeah,
one?
that's the one.
All right.
Got a quick one while we
Sure.
Yeah, go ahead, Brad.
Have you set up, or are they planning to set up any kind of promotional materials, educational materials at the park for them to QR code, download the app? Is that coming?
We haven't gotten that far yet. Honestly, well, for one thing, COVID's been a real stick in the mud here. So we're supposed to spend a lot of time over on the Big Island, interacting with the park and having more of these two-way conversations, and that's really honestly gotten away, of course. But yeah, I think it's a great idea. One of the ideas I had is I would like to just have a couple of iPads sitting there in the park, a table like this. Maybe they're like chained like they are in the app, and like the Apple Store would be in there, right? They're like tethered or something, so people can walk away with them. But they have a couple of iPads with the app loaded up, and they're already preloaded with the app, and it's kind of turned on and locked, and so they just point it at the table, and the models are sitting there on the table, and they can walk around with it and check it out and explore. Any other information just from the park's perspective they want in there? It's easy to add sites or information. So, park in general.
I'm gonna take turns between the online and the room, but I'm not currently seeing online, so I'm gonna go in the room again. Maya.
Thanks, Phil, for your talk. So super cool. I have a question about the clustering. And I'm curious if eventually, or maybe you've already done this, you'll look at clustering between sea level rise stuff, tidal stuff, and then rainfall. And I can't help but to get curious because of this Kona low we had, and then some places were reporting 14 inches in one day. If that happens on the day of a Phrygian spring tide, what does it mean?
Yeah, no, I think that's a really great question, and that's kind of, I would say, in terms of sea level rise impacts, sort of cutting edge question in my opinion, is how do you get this? Is the compound flooding, right? And how do you marry those two together, because they're very different quantities, sea level and precipitation. You really need some sort of drainage basin model to be able to model where does precipitation go, and then how does it even get into the storm drains. And I know that Chip's group, I think he was online. They've done some work with just groundwater and understanding the drainage system. So maybe there's some synergy there, but it's a big question. You could do some statistics of just understanding if you get an extreme rainfall and you get an extreme sea level. And actually, Math and Landscape School Center is doing some of that in the Pacific. But in terms of getting an actual water level, total water level out of those two, that's pretty tricky. But I think it's definitely something that we want to.
Another question in the room now.
Yeah, first off, it's an incredible model. Blown away, not only by the app, just by your modeling in general. I was curious though, when you were showing what was going to happen early in the century and mid-century between the four places you had, Hawaii, Guam, they were quite different. And that kind of, and I followed your description, but I wasn't quite sure why they were so different. I mean, Hawaii had a little drum, and none of the others did, for example.
Oh, you mean in the climatology plots. We're
Yeah.
looking throughout the year.
Yeah, yeah, yeah.
Well, yeah, there's different seasonal cycles around, just the way that the seasonal cycle moves around the Pacific Basin. Some places are at sort of a node and they just don't get much of that. Kwajalein doesn't get much of a seasonal cycle, and so that's part of it. Their tides also don't have a strong seasonal component, so theirs is fairly flat throughout the year. Yeah. I mean,
So
it
then
really-
is there spatial separation on the globe that's having an impact on that? Difference in there.
Certain latitude plays a big role, just the latitude that these locations are and how much. The further you go away from the equator, obviously the more seasonal cycle you get in mean sea level, right? Then of course the tides are a little more complex than that.
Awesome presentation. Thank you.
We do have a question online, Heather.
Hi, thanks, Phil. You've successfully raised my fears for sea level in 2030s. So I don't know if I appreciate that actually, but yeah, thanks for the good explanation. I did just would like to hear about the transferability of the app. So I know how much effort it's taken to get the data you need and to build the app for the Puho park, but what are the opportunities for expanding that?
That's probably a question for Jeff and Dean if they're online, because really the key component there is really the amazing data set they put together that underlies it. And that's the real effort. There was a lot of effort that went into building the app, but now that it's built, there's a workflow that exists now to then incorporate other DM information into that. There's obviously other ideas we have, but in terms of like the portability of it, it really relies on the information that topographic imagery.
Jeff and Dean, I heard Phil throw you on the hot seat there.
Sorry.
Any response?
Go ahead.
All right. I'm going to say no, not at this time, but that's a really good question, and I think of interest to a lot of folks as to how that can be built out, expanded, and utilized. Frankly, not just in Hawaii and the Pacific, but I think at least most of us on this call certainly have a deep focus in Hawaii and the Pacific. We have another moment or two if there's any final questions, either online or in the room. Otherwise, we're gonna, our friend here. Yep,
I have a question.
yep, thank you.
So this information is really good. I taken oceanography, but haven't learned much about the wobble and these cycles as well as a marine biologist. And I know that there are a lot of efforts to try to get science curriculum up to speed throughout the Pacific and in Hawaii that are place-based. And this seems really relevant, especially when you're talking about the climate narrative, the disasters of what you should be concerned of, and then you pointing out the cancellations, because I know this recent Phrygian tide cycle, it was pretty high, but it wasn't as impactful as we've seen in other years. And so then you get people go, oh, it's not, then climate change isn't a big deal. But this kind of knowledge is really important to share with the public and with students who want to do something and better understand it. So are you or your team working with educators in curriculum development to just get at least this baseline knowledge?
No, we haven't at this point. But I think even the tool, this AR app, is another good opportunity to do that, right? And maybe there are other things we could add to it, other informational sections that not just seeing the map, but also talking about the tides and the specific local knowledge that goes into making decisions like that. Yeah, it's a really good point. We haven't done much of that, but definitely.
Cool if they had little lectures on YouTube, that teachers could use in class.
I highly recommend connecting with Shereel and Emily Sesno, who are part of the PICASC team doing curriculum development.
Great idea. Cool. Yeah.
I see Emily's online.
They're both there.
Yeah, I see they're online with us. And then we also have, and pardon me, Richard, if you go by Dick or Richard, I apologize, but you have your hand up, so please take the mic.
Hi, yeah, Rich Mckenzie. My dad was Dick. I'm Rich.
Right.
But thanks, Phil. That was a really incredible presentation, and really learned a lot about how wobble affects the tides. This is more like I guess a comment, and your research highlights the importance of monitoring across the Pacific in terms of, how are the variability in terms of how the high tides will fluctuate over these years, and what does that mean for coastal processes? So how will, we focus on mangrove forests and how they respond to sea level rise. So what does this mean for them? Will there be greater wave action when the water is deeper, so there'll be higher erosion? And then when the levels are lower, will there be some response from the mangroves to somehow compensate for that? So just really, thanks for sharing that, and really gets me motivated to keep pursuing monitoring mangroves across the Pacific and other coastal ecosystems as well.
Yeah, no, it's really important work. And so if you want to reach out and keep that conversation for that.
All right, Rich, thank you for that question. Thank everybody for the questions. Thank you, Phil, for your excellent presentation and this really cool app. And being, as Phil recognized, although a little too late, when he walked in the room, he said, wait, I'm gonna be a guinea pig, aren't I? Well, yeah, kind of. Thanks, everybody, for bearing with some of the troubleshooting and things. We're really moving forward to improve and be successful. And what we see is perhaps the rest of our lifetimes of running hybrid meetings and having people in the room and online. So a round of applause for Phil. Thanks.
Oh, clapping, thanks.
Yep. Yeah, and a lot of clapping online too. Thank you, everybody, for taking the time joining us. We're going to see you in January. This is the first Tuesday of the month, except for January, because it's so close to New Year's and all that. We'll be sending out messaging, but we're going to go to the second Tuesday of the month. We've got our very own Romina King joining us to give a presentation on all the cool stuff at the University of Guam and in that part of the world. So thanks. Have a great one.
Thanks, everybody.
Thank you.